Welcome back. In the last topic, we discussed covalent compounds and how they may or may not dissolve in water. Now, let's have a look at ionic compounds and how they may or may not dissolve in water. Sodium chloride, when you put it into solution, on its own is not polar, that's not going to help us. But when we place it in water, it has the ability to dissociate. Dissociate means it has the ability to break apart into its two separate halves. So the sodium chloride dissociates, breaks apart into positively charged sodium ions and negatively charged chloride ions. Let's have a look at what happens to those ions now that they're in that water. So here I have a diagram of a sodium ion, which I've coloured in blue, placed in water. I want you to have a close look at that diagram and see if you notice anything about the sodium ion and about the water around it. Have you spotted anything of interest? I'll tell you what, I'll give you a hint. I'll put up the chloride ion as well, the anion, so that you can have a look and see if you notice any pattern, any distinction between the two. What I'm hoping you've spotted, if you have a look at the water molecules arranged around the sodium cation, that sodium cation has a positive charge, and you'll notice that all of the water molecules have the oxygen, the negative end of the molecule, pointing towards the positively charged cation. We call this hydration. Those waters are attracted to that positively charged cation. In particular, the negative end of the water is attracted to the positive cation. So the waters surround that cation and they help hold it in solution. They stop it from wanting to snap back together with that chloride ion. If they're able to do this, they can keep that sodium ion in solution. They can keep it dissolved. Come over to your chloride ion, have a look. In particular, have a look at your water molecules. You'll see that they're turned around. They're facing the opposite way. You've got your chloride anion with a negative charge in the middle, and the waters have their hydrogen end, their positive end, all facing that chloride ion. Again, they are attracted to that negatively charged ion, and they surround it, they keep it hydrated, they keep it in solution and prevent it from falling back out. So we can take a neutral substance like sodium chloride, and by putting it into water, break it up into charged cations and anions, which water can then keep hydrated and dissolve. And once again, this only happens because water is a polar molecule, positive at one end and negative at the other, and that's what allows it to keep these ions in solution. You may recall a bit of a running theme we've had together. I've been asking you to look for good chemistry jokes. Pretty sure you haven't found any yet. This actually all started a few years ago when a student of mine came up to me in the lab. He said, "Hey Daniel, I've got a joke, you're going to love this, you're going to love this." And what he said to me was, "Why do white bears dissolve in water?" And I think you already know the answer. It's because they're polar. So it's awful, and it's what started all of this mess in the first place. So water will dissolve polar substances or substances that can develop a charge, cations and anions. If they are not polar and they don't have that charge, it's not going to work. It's not going to happen. To round out this topic, you and I are going to look at a few examples together just to make sure we've got the right of this. Let's start by having a look at a video of what happens when we try and put potassium bromide in water. So here I have some water, I've got in a test tube, and to that I'm going to pour in a small amount of potassium bromide, and we'll give it a good mix. And you can see that that potassium bromide, that neutral compound, has dissolved. So if it's dissolved, there must be a reason for it. Let's come back and have a look at that. So you can see here on the left, just got a reminder there that our solid potassium bromide has dissolved for you. That potassium bromide dissolves because that solid material is able to, when in water, break up into cations and anions. The water then hydrates those ions, it surrounds them and wraps them up because it's attracted to them and keeps them in solution. It prevents them from feeling they need to snap back together. So as long as the water can keep doing this, we can dissolve potassium bromide. We can make a potassium bromide solution. Want to have a look at another example? Let's try copper nitrate. So once again, the same setup. I've got a test tube with water in it. Sprinkling in a little bit of copper nitrate, this blue powder here. And you can see that with a bit of shake, bit of work, we can get that solid copper nitrate to dissolve in water. You can see the appearance of a blue-coloured solution. That blue colour has come around because those copper ions have dissolved. That blue colour, very distinctive of copper in solution. Once again, let's come back and have a look at why this might have happened. Like the previous example, you can see that my copper nitrate, my solid material, has gone into the water and it has dissociated. It has broken apart into copper cations and nitrate anions. And once again, those polar water molecules can then wrap around those ions, keep them in solution and keep them soluble. And that's why we can make a copper nitrate solution. Yeah? That's a couple of ionic compounds. Let's look at some covalent compounds. Let's look at some molecules as examples. See what they do, see how they behave. First, let's have a look at what happens when we put acetone in water. You may have heard of acetone. It's a common ingredient in some nail polish removers. But here we are, just adding a few drops of acetone to the water in our test tube. And you can see that when I give it a bit of a shake, these two have mixed together perfectly. It just looks like there's one liquid, one solution there. That means the acetone must have dissolved in that water. Let's have a look at why. Here on the right-hand side, I've got the covalent compound. I've got the Lewis structure for acetone. And we notice immediately this is a covalent compound, not an ionic compound, so I can't break it into cations and anions. That can't be what's happening here. Instead, I want you to notice that oxygen is a very highly electronegative element, really wants the electrons, whereas your carbon and hydrogen are not as electronegative. So the oxygen pulls the electrons to one end of the molecule and we end up with a polar molecule. Slightly negative end, slightly positive end. Polar molecules will dissolve in water because water is polar too. So acetone will dissolve in water. Once again, a chemical reaction just to show that liquid acetone dissolving in water to make aqueous acetone. One more example, let's have a look at what happens when we put hexane, a long hydrocarbon chain, just hydrogen and carbon atoms, in water. So back into the lab, I've got a test tube which contains some water, and we're going to add a few drops of hexane. And if you have a really close look, you've got to use sharp eyes for this, what you can see is you can see a small line, you can see a layer in the solution. The reason you can see a layer is, despite our best attempts, the water and the hexane refuse to mix with one another. So the water is sitting on the bottom layer, and then sitting on top of that, we have the hexane. Once again, let's go back. Let's try and explain why that might be happening. So in this photo, I'm hoping you can very clearly see that distinction, that layer there, showing that the two refuse to mix with one another. Why is that the case? Once again, water is a polar molecule, negative at one end, positive at the other. But hexane, this large molecule here, is made of just carbon and hydrogen. Very similar electronegativity in the two atoms, the carbon and the hydrogen. It's a non-polar molecule. So if water has a positive end and a negative end, but hexane, this long hydrocarbon, has no positive and negative end, there will be no attraction, no affinity from one to the other, which means they will not mix and they will not dissolve. And that's why the hexane will prefer just to sit on the top on its own. It's perfectly happy that way. Right, big topic for us today. What have we covered? We've talked about dissolution reactions, about how we get chemicals to dissolve in water. We've talked about ionic compounds and the fact that they can dissolve in water by dissociating, by breaking up into cations and anions, which are then attracted to the polar water molecules. We've also talked about the fact that polar covalent compounds will also feel an attraction for water and be allowed to dissolve. In our next topic, we're going to explore what happens when hydration isn't strong enough. What happens when that attraction between water and a cation just isn't sufficient to keep it dissolved. See you then.